This is Dr. D. Govardhan, Professor in the Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today, we are discussing the tutorial question bank on Module 3, Centroid, Central Gravity and Moment of Inertia in Engineering Mechanics. Here now we are taking one problem to determine the central gravity of T section. It is also treated as a composite section. Before solving the problems, check the given figure whether it is symmetrical about the vertical axis or horizontal axis or both the horizontal and vertical axis, or it may not be symmetrical about any line. Here this problem is symmetrically about the vertical axis, hence that axis is treated as one of the reference lines to determine the central gravity of the T section. Another reference lines, we have to take it as horizontal line passing through the bottom of the figure, that is the EF line shown in the figure now. So with respect to these two lines, we have to identify the position of central gravity of the composite section. Since the object is symmetrical about the vertical axis, the central gravity always lies on this line's vertical line. That means we have to represent only the coordinate of y. X coordinate is treated as 0 values. Okay, determination of y coordinate of the central gravity. First of all, let us divide this composite section into number of sections such that each part is representing a regular figure, such as it may be the rectangle or square, triangular section, semicircle, circle and so on, depending on type of the problem. But here we can divide this object into two sections as A, B, C, H now, and another one is G, D, E, F now. That is, we can represent in the symmetrical section, that is T section, into two rectangles now, A, B, C, H and D, E, F, G now. So here the problem is the position of the center of gravity can be written by using the equations. Y c is equal to A1 plus A1 Y1 plus A2 Y2 divided by A1 plus A2 now, where A1 and A2 is representing the area of the cross section of two rectangles. Here it is the 1 and one more is the 2, and Y1 and Y2 are representing the position of its centroid with respect to the reference lines. So by using these relations, we can determine the position of central gravity of the composite section. Here A1 is equal to, for the first figure, the area of the first rectangle is 30 into 100, it is equal to 3000 mm square. Similarly, the position of the centroid for the rectangle always lies it is symmetrical line here now. The total height is given 150 minus 30 by 2, 150 minus 30 by 2, it is equal to 135 mm. Similarly, for the rectangle 2, EFDH, the area is again given by, the breadth is given here, it is equal to 30, the die is given, it is equal to 150 minus 30 is equal to 120, hence area is equal to 120 into 30 is equal to 3600. The position of the centroid is again in the middle of rectangle 2 now, that is 120 by 2, it is equal to 60 mm. So by using the relations, Yc is equal to, that is position of the centroid of the composite section with respect to the reference lines, that is x-axis is given by A1 plus A1 Y1 plus A2 Y2 divided by A1 plus A2 and substituting the values of A1 Y1 and A2 Y2, we got YC is equal to 94.1 mm. That is from the bottom position, it is at a distance of 94.1 mm. That is representing the YC now. That is the XC is equal to 0, YC is equal to 94.1 mm. Okay, this is representing the position of centroid of the given T section. Now for the second problem, the centroid of the unequal angle section 100 by 80 by 20 mm as shown in figure 2 now. So like in the previous problems, it is not at all symmetrical about the vertical or horizontal lines. Hence, the horizontal line which is passing through the bottom of the figure is treated as the x-axis. Similarly, the bottom of the left hand side vertical line it is treated as the y-axis for this figure now. With respect to these two reference lines, we have to find the center of gravity of composite section, that is here L now. Now divide this composite section into minimum number of regular figures. It may be the rectangle, square, triangle, circle, semicircle, quarter circle and so on. But here we can divide it into two rectangles as represented here 1 and 2 as shown in figure now. For the rectangle 1, the area is equal to 100 by into 2 equal to 2000 mm square. X1 is equal to, here it is representing, here the position is given now. For this one, here 1 and 2, here it lies on this line now. X1 is equal to 20 by 2, it is equal to 10 mm. Similarly, Y1 is equal to, height is given 100 mm, 100 by 2 is equal to 50 mm now. Similarly, A2 is equal to, second one, that is 80 minus 20 is equal to, into 20, it is given. X2 is equal to, again, it is given now. Totally 20 plus remaining 60 by 2, it is equal to 50 mm. Y2 is equal to 20 by 2, it is equal to 10 mm. Substituting the values, the equation XC is equal to A1 X1 plus A2 X2 divided by A1 plus A2, and substituting all the values we got, it is equal to 25 mm. Similarly, the distance between the center of gravity of the section from the bottom of the figure, that is y coordinate is given by y is equal to A1 Y1 plus A2 Y2 divided by A1 plus A2. From this relation we got YC is equal to 35 mm. Similarly, for the figure number 3, a uniform lamina shown in figure consists of a rectangle, a circle and a triangle. Determine the center of gravity of the lamina. All the dimensions are in millimeters. Here the reference line is already taken. That is, we have to determine the center of gravity of this composite figure with respect to the x-axis and y-axis as shown in figure now. This is x-axis and y-axis now. Here it is divided into 3 segments now. 1, 2 and 3. One is the semicircle, the second one is a rectangle, third one is a triangle as shown in figure now. For the rectangle, here this one now, the length is given 100 mm and 50 mm is height is given now. That is 100 into 50 is equal to area is equal to 5000. The center of gravity always lies here symmetrical line. That is the x1 is equal to, we can take it as a 25 plus 100 by 2. It is equal to 75 mm. Similarly, y is equal to half of 50 mm. It is equal to 25 mm. Similarly, for the semicircle now, area is equal to pi r square by 2, which is equal to 982 mm square. X2 is equal to, here from the base it is equal to 4r by 3 pi. But we required from this position now, hence r minus 4r by 3 pi, r is equal to given 25 mm, hence this value is equal to 14.4 mm. And y is equal to, it is a symmetrical about this one now, it is equal to 25 mm. Similarly for the triangle, here it is there, the center of gravity always lies at a distance of h by 3 from its base now. Hence, here it is symmetrical about the vertical line. Now x coordinate is equal to, here we have taken total here 125. Here it is given 25 into 25, which is equal to here 100 mm. That is the 125 minus 100 mm. And y3 is equal to 50 plus again h by 3. H is equal to given 50 mm. Hence, it is equal to 67.7 mm. Now substituting all the values in the given equations, xt is equal to a1 x1 plus a2 x2 plus a3 x3 divided by a1 plus a2 plus a3. And substituting the values, we got xt is equal to 71.1 mm. Similarly, yc is equal to, and substitute the values of all the values in the equation a1 by 1 plus a2 by 2 plus a3 by 3 divided by a1 plus a2 plus a3, we got it is equal to 32.2 mm. This is representing the position of the centroid for the composite section, having combination of semicircle, rectangle and triangle. Now center of gravity of a rectangular section is a circle section is given, but it is in the form of hollow, it is given. Here the problem is a square hole is punched out of circular lamina. The diagonal of the square being the radius of the circle as shown in figure. Find the center of gravity of the remainder if r is the radius of the circle now. Okay, this object is now divided into two parts now. That is symmetrical about the horizontal axis given now. That is AB, the diameter is nothing but x axis now. Here A1 is equal to, that means here the vertical line, that is the coordinate of y is always lies on this line only. That is yc coordinate is equal to, here in this question we can take it as 0 only. Only x coordinate we have to take it now. Here the area of the main circle is equal to pi r square. Similarly, cut off square is equal to 8 is equal to r into r by 2 is equal to 0.5 r square. Xt is equal to r plus half of the radius is equal to 1.5 r. And substituting the values xt is equal to, we are having a1 x1 minus a2 x2 divided by a1 minus a2. This minus is representing the area is negative now. So on substituting all the values, we got it is equal to 0.05 r now. A semicircular area is removed from a trapedium as shown in figure. All the dimensions are in millimeters. Determine the center of the remaining area. As the section is not at all symmetrical about to any axis now. So, the horizontal line which is passing through the bottom of the figure is treated as the x-axis now. And extreme, the line which is perpendicular to the x-axis and passing to extreme left of the part is treated as a y-axis now. With respect to these two axes, we have to represent the position of its centroid. Now this is represented now, this area is divided into three segments now. Here, like this. One is in the form of rectangle, the second one is in the form of triangle, and the removed area is in the form of semicircular as shown in figure now. So the area of the rectangle is equal to 80 into 30. It is equal to 2400 mm square now. Since it is symmetrical about the x-axis and the y-axis now, the intersection of the symmetrical and represented position of the centroid for the rectangle, hence x1 is equal to 8 by 2 and y1 is equal to 30 by 2, that is the 15 mm and 40 mm respectively. For the triangle, the area is equal to 8 into 30 by 2, half into base into height, it is equal to 1200 mm square, and x2 is equal to here 30 plus the remaining height is there now, that is h by 3, which is equal to 53.3. Similarly, y2 is equal to that h by 3 from its base r to h by 3 from the reference lines, which is equal to 40 mm. Semicircle, since here now area is given, half of the circle is equal to pi r square by 2, it is equal to 628.3 mm square. x3 is equal to, here it lies at this position now, that is 40 plus 40 by 2, it is equal to 60 mm, and y3 is equal to, it is lies on symmetrical lines at a distance of 4r by 3 pi, which is equal to 8.5 mm. So the center of gravity of composite figure, that is the trapezium, is obtained by the relations a1 x1 plus a2 x2. Here minus of a3 x3, minus is representing the area is removed here now, area is treated as negative, divided by a1 plus a2 minus a3, which is equal to 41.23 mm. Similarly, yc is equal to a1 y1 plus a2 y2 minus of a3 y3 divided by a1 plus a2 minus a3, which is equal to 26.5 mm. Okay, till now we discussed the center of gravity of or the centroid of plane figures. Now, for the solid bodies, the area is replaced by the mass if it is represented with the different materials. If the composite section is made up of the same materials, the area is replaced by the volumes now. Here the volume of few solid bodies are given as now. Volume of the cylinder is equal to pi r square h. Volume of hemisphere is equal to 2 by 3 into pi r cube. Volume of right circular solid cone is equal to 1 by 3 pi r square h. A solid body formed by joining a base of right circular cone of height h to the equal base of right circular cylinder of height h, small h. Calculate the distance of center of mass of the solid from its plane face. When h is equal to 120 mm and small h is equal to 30 mm. Now, observing this body, it is symmetrical about the vertical line now. Hence, this vertical line is treated as a position of one of the reference line now. That is the y-axis. The line which is passing through the bottom of the figure is treated as now another reference line x-axis now. Now, the first determine, since it is made up of same materials, not mention anything now. Hence, assume the cylinder as well as the right circular cone both are made up of same materials. Hence, by determining the volumes, we can determine the position of center of mass or the center of gravity. Both are here treated as the same as the gravitation field is uniform now. So, the area of the volume of the first to be the cylinder is equal to, that is given now, pi r square h now, pi r square into h, which is equal to 30 into pi r square. Similarly, x coordinate is equal to 0 because it is symmetrical about the y axis now. y is equal to, it is half of its height, it is equal to 15 mm. Similarly, for the right circular cone, the area is equal to 1/3 of pi r square h, which is equal to 40 pi r square mm cube now. And y is equal to, again now, here it lies at a distance of h by 4. H is equal to 120, but we are measuring from the bottom of the cylinder, hence 30 plus 120 divided by 4 now. So which is 30 plus 125, 4 is equal to 60 mm. So the distance between center of gravity of the section from the base is given by y is equal to v1 y1 plus v2 y2 divided by v1 plus v2. And substituting the values of v1, v2, y1 and y2, finally we got the yc position is given 40.7 mm. That is the center of gravity lies at a distance of 40.7 mm from its base now. Now problem number 7. A body consists of right circular solid cone of height 40 mm and radius 30 mm, placed on a solid hemisphere of radius 30 mm the same materials. Find the position of center of gravity of the body. Again, this object is when observing now, it is symmetrical about the vertical axis. Hence, the position of the center of gravity on these lines, that is the x coordinate is equal to 0 now. Only y coordinate is enough now. Now, let the bottom of the hemisphere, this is treated as our x-axis now. So we have to identify the position of reference lines. One is already, it is symmetrically, that symmetrical line is treated as y-axis, that is the CD, and the x-axis is representing here now the line which is passing through the bottom of the figure, but in horizontal. So here the center of gravity lies on symmetrical lines, hence the x coordinate is equal to 0, that is the x is equal to 0. We require only the position of yc now. If the volume of the hemisphere is equal to 2 by 3 into pi r square, pi r cube is given. It is equal to 2 by 3 into pi into r is equal to nothing but equal to 30 mm, which is equal to 18,000 into pi mm to the power of 3 now. y1 is equal to 5r by 8 pi into r is equal to 30 divided by 8 is equal to 18.75 mm. The right circular cone is given. The volume of right circular cone is 1/3 of pi r square h. It is equal to 12,000 into pi mm to the power of 3, and y2 is equal to here 30 plus h by 4, that is it is equal to 40 mm. And substituting the values in the equation, yc is equal to v1 y1 plus v2 y2 divided by v1 plus v2. It is used to determine the position of center of mass or centroid or center of gravity of the object now. Since here generally we are using center of gravity as center of mass because it is represented as a solid now. So on substituting these values, we got the yc is equal to 27.23 mm. Okay, moment of inners of standard sections. Is the moment of inertia of rectangle about its central axis, that is the axis which is passing through the centroid here. Now x-axis we are taking, this is the y-axis. I-axis is equal to bh cube by 12. For the triangle, here it is given by bh cube by 36. For the circle, pi d to the power of 4 divided by 16 about its horizontal line passing through the centroid. Similarly, for the semicircle 0.11 r to the power of 4, Ix is equal to Iy because this is nothing but symmetrical about the area equally distributed now. Here both are equal in the case of quarter circle. Ix is equal to Iy is equal to 0.055 r to the power of 4. For the ellipse, Ix is equal to pi a b cube divided by 4. Iy is equal to pi b a cube divided by 4 now. Now we are taking this moment of inertia of composite L section. The moment of inertia, it is represented as the product of area multiplied by the square of the distance between the central gravity of that section from the reference line now. So the units of moment of inertia equal to, if all the dimensions are represented in the form of mm, it is equal to mm to the power of 4. It is only applicable for the area, hence we are calling it as moment of inertia of an area now. When it is the mass is there now, moment of inertia mass is equal to mass multiplied by the square of the distance between the centroid of the two mass from the reference line. Here in figure number 10 now, shows the rectangle A, B, C, D, E, F is the composite figure. Compute the moment of inertia about the area about the axis K now. Here now. Now, since it is a composite section now, first of all, we have to identify the center of gravity now. Okay, for this one now, it is dividing into two sections now. One is representing A, B, C and here D point. Another one is here already A, B, C, D is there now. I am taking another point is now here now H now. Another one is E, F, D, E, F and H are there now. These are nothing but we are dividing this entire L section into two rectangular segments. One is representing A, B, C, H. Another one is D, E, F, H as shown in figure now. The moment of inertia of the section 1 now about the center of gravity parallel to the about its center of gravity is given now. Parallel to the KK is given by B1 D1 cube divided by 12. It is equal to 40 into, that is given, it is equal to 40 into D is nothing but equal to, this area is given 120, it is equal to 120 cube divided by 12 now, which is equal to 640 into 10 to the power of 3 mm to the power of 4 now. Similarly, the distance between center of gravity of the section 1 section, here it is given from the axis is equal to 100 plus 40 by 2, it is equal to 120 mm. Then IKK1 is equal to, it is given Ig1 plus A1 H1 square, because what we measured, this is nothing but representing Ig1 is representing moment of inertia of this entire section about its central axis. So this moment of inertia is to be transferred to the section KA by using parallax theorem. According to the parallax theorem, IKK is equal to, that is the moment of inertia of this entire section about the KK line is given by the sum of moment of inertia of this part 1, section 1 about central axis and the product of area multiplied by the square of the distance between the two parallel lines. So by using this parallax theorem, the moment of inertia of the first section is obtained as now Ig1 plus A1 H1 square now. Ig1 is equal to, already we determined 641 into 10 to the power of 3 now, plus area is equal to 120 into 40 plus the distance between these two is equal to 120 square now, which is equal to 69.76 into 10 to the power of 6 mm to the power of 4 now. Similarly, the moment of inertia of the section 2 about the center of gravity and parallel to the x-axis, that is, we have to determine this direction, the parallel now. Here in this case, the distance is given now. The distance between center of gravity of the section 2 and kk is equal to 100 plus 240 divided by 2, it is equal to 220 mm now. It is represented here now h2 now. Similarly, the moment of inertia of this rectangle about the vertical axis of symmetrical lines, it is given by b2 d2 cube divided by 12. Here b is nothing but representing now b2 40. It is dividing just 1 240 whole cube divided by 12. It is equal to 46.208 into 10 to the power of 6 mm to the power of 4 now. So the moment of inertia of this entire section 2 about the kk line, I assume I kk2 according to the parallax theorem, Ig2 plus A2 into H2 square now, and substitute the values we got I kk2 is equal to 510.72 into 10 to the power of 6 mm to the power of 4 now. The moment of inertia of entire section, that is the 1 and 2 about the kk line, is obtained with the summation of I kk1 plus I kk2, which is equal to 580.48 into 10 to the power of 6 mm to the power of 4. Now the moment of inertia of composite section, that is here L section we are taking, about the central axis, x and y axis of the angle section as shown in figure. The central axis means the axis which are passing through the center of gravity of the given object or the given plane area. Since it is the L section now, it is a composite section. Moreover, it is not at all symmetrical about the vertical line or horizontal lines. Hence, the line which is in horizontal passing to the bottom of the figure is treated as the x-axis now, and the extreme left is treated as the vertical line is treated as the y-axis. So, with respect to these two lines, determine the position of its centroid. So, for the rectangle 1 now, the area is equal to 100 by 2, which is equal to 2000 mm to the power of 2 now. Similarly, x1 is equal to, here, this one, it is equal to 20 by 2, it is equal to 10 mm. Similarly, y1 is equal to 100 by 2, it is equal to 50 mm. Similarly, for the section 2, we have taken area is equal to 60 into 20, that is 20 plus 80 by 2 is equal to 60, y2 is equal to 20 by 2, it is the position of x2 and y2, area is equal to 80 minus 20 into 20 is equal to 1200 mm square now. So, substituting the values in this equation, so yc is equal to a1 y1 plus a2 y2 divided by a1 plus a2, that is yc we got to 35 mm, that is it is at a distance of, we take like this 35 mm, this is nothing but position of horizontal line which is passing through the centroid now. Similarly, xc is equal to a1 x1 plus a2 x2 divided by a1 plus a2, we got from this equations xc is equal to 25 mm. So, here 25 mm, it is equal to 35 mm, this is the representing position of the CG for the L section. It is not at all lies within the figure now. Here XC and YC now. This is the position of centroid now. Now for the rectangle 1 now. The moment of inertia of rectangle 1 about an axis passing through its centroid, that is the x-axis is given by Ix1 is equal to Igx1 plus A1 Hx1 whole square, where Gx1 is representing the moment of inertia of first section about its central axis, which is equal to 20 into 100 cube divided by 12 now. It is equal to 1.67 into 10 to the power of 6 mm to the power of 4 now. The distance between center of gravity of the rectangle from the, here it is given coordinates are now 25 into 35 mm. So it is given, it is equal to IGX1 and HX1 is equal to, we got it now, 50 minus, because this height is equal to 50, here it lies at this position now, it is given 35, 50 minus 35 is equal to 15 mm. Similarly, the moment of inertia of rectangle about the x-axis is given by IXS1 equal to IGX1 plus A1 HX1 whole square. Substituting the values of IGX1 is equal to 1.667 into 10 to the power of 6 plus A1 is equal to, given now, the area of the first rectangle is given, it is equal to 2000 and HX1 is equal to 15 square, and substituting these values we got to 2.117 into 10 to the power of 6 mm to the power of 4 now. For the rectangle 2 now, the rectangle, here the CG is given, already we identified, it is equal to, the coordinates are given now 25 and 35. For this coordinate is equal to, here it lies somewhere, it is there, which is equal to 10 mm, x coordinate, y coordinate 10, x coordinate is equal to 20 plus 60 by 2, it is equal to 50 mm plus and 10 mm. Now from this relationship we got to HXT is equal to, here where IGXT is representing the moment of inertia about its central axis, which is given 60 into 20 cube by 12, which is equal to 0.04 into 10 to the power of 6 mm to the power of 4 now. And HXT is equal to, that is the x coordinates is given by, that is this height when we are taking now, it is equal to 35 minus 10 is equal to 25 mm. Similarly, on substituting this values IXT is equal to IGX2 plus A1 HX2 whole square, we got it is equal to 0.79 into 10 to the power of 6 mm to the power of 4 now. So IXS is equal to, we got total moment of inertia possessed by this entire composite section, it is equal to sum of this moment of inertia possessed by this 1 and 2 about the horizontal lines, which is equal to 2.907 into 10 to the power of 6 mm to the power of 4 now. Similarly, the y section is given by IY1 is equal to IGY1 plus A1 HY1 square now. IGY1 is nothing but representing the moment of inertia of first sections about the its central axis, that is nothing but here about these lines when we are taking like this y axis, which is equal to 100 into 20 cube divided by 12, 0.67 into 10 to the power of 6 mm to the power of 4, and these coordinates already we determined it is equal to 25 into 35. The coordinates of the first block is given by, that is the x1, y1, it is equal to 10 and 50 mm is given now. So in this case, hy1 is equal to, that is the measured from the vertical lines like this, it is equal to 35, here it is given 25, it is given 10, no? Hence 25, 10 difference is equal to 15 mm. And substituting the values y1 is equal to ig1 plus a1 hy1 whole square, and substituting these values we got to 0.517 into 10 to the power of 6 mm to the power of 4 now. For the second object now, here the here it is given, the coordinates are assumed just x2, y2, it is equal to, x2 is equal to 50 and 10, but we are measuring just parallel to this line, here 10, no? It is given parallel to the y-axis like this. This y coordinate nothing but x values we have to take the difference, which is equal to here now 50 minus 25, it is equal to 25 mm. That means Ig/Y2 is equal to 20 into 60 whole cube divided by 12 is equal to 0.36 into 10 to the power of 6, where Ig/Y2 is representing the moment of inertia of the second section about the vertical lines, and Hy2 is equal to, already I told 50 minus 25 is equal to 25 mm. Substitute the values I/Y2 is equal to Ig/Y2 plus A2 Hy2 whole square. We got 1.11 into 10 to the power of 6 mm to the power of 4. The moment of inertia possessed by these composite sections about the y-axis is obtained by the summation of moment of inertia possessed by the first and second section about the y-axis, which is equal to Iy is equal to 0.517 10 to the power of 6 plus 1.11 into 10 to the power of 6. Its value is equal to 1.627 into 10 to the power of 6 mm to the power of 4 now. Find the moment of inertia of T section with the flange as 150 mm by 50 mm and web is equal to 150 mm and 50 mm about the x-axis and the y-axis through the center of gravity of the section. So in this case again we have to determine the position of the centroid of this composite section. While determining, first of all identify the position of reference lines now. Here this object is symmetrical about the vertical lines, hence it is treated as the vertical line is treated as one of the reference line, that is y-axis. The x-axis is here now representing the horizontal line passing through its bottom position. Now split the sections into two rectangles 1 and 2 as shown in figure. Rectangle 1, the area is equal to A1 is equal to 150 by 50 is equal to 7500 mm square. H1 is equal to, is given 150 plus 50 by 2, 175 mm. For the rectangle 2, it is equal to 150 into 50, it is equal to 7500. And H2 is equal to 150 by 2 is equal to 75 mm. Since it is a symmetrical about the vertical lines, the x coordinate is treated as a 0 now. Hence only we have to determine the position of its y coordinate, which is equal to A1 y1 plus A2 y2 divided by A1 plus A2, which is equal to 125 mm. The moment of inertia about the x-axis now, 125 mm, it is given. Here it is treated as the x-axis and the y-axis. These are called central axis, that is the axis passing through its central gravity. The moment of inertia Ixx1 is equal to our first element now. This is nothing but here central axis now. This is the x-axis and the y-axis. As in these are nothing but central axis, that is xc and so on. Now according to the parallax theorem, the moment of inertia of first section about the x-axis is obtained by using the relation Ixx1 is equal to Igx1 plus A1 Hx1 whole square, where Xx1 is representing the centroid of that is section 1 about the x-axis. It is equal to sum of moment of inertia about its central axis passing through its central gravity. This is known as Igx1 plus A1, that is the area of the first rectangle. The distance between these two lines is represented as Hx whole square. Hx. By using these relations now, we got Igx1 is equal to 150 into 50 cube divided by 12, 1.56 into 25 multiplied by 10 to the power of 6 mm to the power of 4. The distance between central gravity of rectangle 1 and with the x-axis is equal to 175 minus 125. Here it is given total length is equal to 150 plus 25, it is equal to 175. but its center of gravity is given, how much is already we determined. It is equal to 125. The difference is nothing but 125 mm. The difference is equal to 175 minus 125 equal to 50 mm. Ixx1 is equal to Igx1 plus A1 H1 square, which is equal to 20.3125 into 10 to the power of 6 mm to the power of 4. Similarly, Ixx2 is equal to Igx2 plus A2 Hx2 whole square, where Igx2 is representing the moment of inertia of section about its x-axis. Now, it is obtained by 50 into 150 cube divided by 12, 14.0625 into 10 to the power of 6 mm to the power of 4. The distance between center of gravity of second section from the center of the whole section, 125 minus 75 is equal to 50 mm. So, by using the relations, Ix is equal to Igx2 plus A2 Hx2 whole square, we got this value is equal to 32.815 into 10 to the power of 6 mm to the power of 4 now. The moment of inertia of composite sections about the x-axis is given by the sum of the moment of inertia possessed by the first section and second section about the x-axis, which is equal to 53.125 into 10 to the power of 6 mm to the power of 4 now. Similarly, the moment of inertia about the y-axis now, here the coordinates of that is the separation is 0 because this object is symmetrical about the y-axis now. Hence, first of all, we have to determine the moment of inertia of first sections about the y-axis, which is equal to 50 into 150 cube divided by 12, 14.0625 into 10 to the power of 6 mm to the power of 4. H1 is equal to 0 because both are constant with each other now. For the second rectangle, the moment of inertia is given by it is equal to 1.2625 into 10 to the power of 4 mm to the power of 4. So, the moment of inertia of these two sections is obtained 14.0625 into 10 to the power of 6 plus 1.5625 into 10 to the power of 6, which is equal to 15.2625 into 10 to the power of 6 mm to the power of 4 now. The moment of inertia of here I section, it is made up of 3 rectangles as shown in figure. Find the moment of inertia of the section about the horizontal axis passing through the center of gravity of the section now. Here this object is again symmetrical about the y-axis now. That is treated as one reference line. The line which is a part passing through the bottom of the figure in horizontal treated as the x-axis and y-axis, and determine the position of centroid by using the relations of yc is equal to a1 y1 plus a2 y2 plus a3 y3 divided by a1 plus a2 plus a3. So, a1 is equal to, first rectangle is equal to 16 to 20 is equal to 1200 mm square. Y1 is equal to, that is the position of the centroid from the bottom is given 20 plus 100 plus 20 by 2, which is equal to 130 mm. Rectangle 2 is given now. The area is equal to 100 multiplied by 2 is equal to 2000. And the position of centroid is equal to 20 plus 100 by 2, it is equal to 70 mm. For the rectangle 3 now, area is equal to 100 into 20 is equal to 2000 mm square, and the y2 is given by nothing but here 20 by 2, it is equal to 10 mm. By using the relations of AC is equal to a1 y1 plus a2 y2 plus a3 y3 divided by a1 plus a2 plus a3, we got yc is equal to 60.8 mm. That is the position of the centroid lies at a distance of 68.8 from the bottom position. This is treated as the GG position. The moment of inertia of the composite section, that is the first section about the x-axis, is obtained by here now. Igx1 is equal to, that is its section nothing but here about this one now, 60 into 20 cube divided by 12, it is equal to 40 into 10 to the power of 3 mm to the power of 4 now. The distance between the central gravity of the first section from the central gravity of the whole section is equal to, here it is given CG is equal to, we got 60.8. It is equal to y1 is equal to, we got 130. So the difference is equal to, we got hx1 is equal to 130 minus 68.8 is equal to 69.2 mm. So Ixx1 is equal to Igx1 plus A1 Hx1 whole square, and substitute the values we got Ixx1 is equal to 5786 into 10 to the power of 3 mm to the power of 4 now. Similarly, for the second object now, Ixx2 is equal to Igx2 plus A2 Hx2 whole square, here which is equal to, from this relationship we got Igx2 is equal to 20 into 100 cube divided by 12 is equal to 1666.7 into 10 to the power of 3 mm to the power of 4 now. Hx2 is equal to the position of centroid of second object from the centroid of composite section. It is given as 68.8 already we determined. It is equal to 70 mm we have taken now. So the difference is equal to 70 minus 60.8. It is equal to 9.2 mm. So Ixx is equal to Igx2 plus A2 Hx2 whole square. We got 1836 into 10 to the power of 3 mm to the power of 4 now. For the third one now, already it is given now 68.8. It is given at a distance of 10. The difference is equal to 60.8 minus 10 is equal to 50.8 mm. That is Hx3 is equal to, Igx3 is equal to 100 into 20 cube divided by 12, which is equal to 66.7 into 10 to the power of 4. So the total Igx3 is equal to Igx3 plus A1 Hx3 whole square, and substitute the values of Igx3 area and the square of the distance. We got 5228 into 10 to the power of 3 mm to the power of 4. So the moment of inertia of entire sections, that is 1, 2, 3, about the x-axis is given by the sum of Ixx1 plus Ixx2 and Ix3. We got 12,850 into 10 to the power of 3 mm to the power of 4. Okay, the moment of inertia of hollow section now. When the moment of inertia of hollow section shown in figure, about an axis passing through its central gravity and parallel to the x-axis now. Here it is a symmetrical about the vertical lines. As in, this is the position of x-axis and y-axis. Hence, we have to determine only y coordinate to determine the position of the centroid of the hollow sections. As in, now it is divided into two parts now. One is the rectangle, one more is the removed circle 2. The area of the first rectangle is equal to 300 into 200. It is equal to 60,000 mm square now. Y1 is equal to half of height is equal to 150 mm. Similarly, the circular hole, that is the removed hole, area is equal to pi by 4 d square, which is equal to 17,670 mm square now. Y1 is equal to, the position is given now. It is equal to this position. It is 100 mm is given from the top. That is the 300 minus 100 is equal to 200 mm. So the position of the centroid of the composite section is obtained A1 Y1 minus A2 Y2 divided by A1 minus A2. This minus is representing the area is removed from the composite figure now. So we got it values is equal to 129.1 mm. The moment of inertia of first sections about the x-axis is given by about its x-axis, that is at a distance of 150 mm. It is given by 200 into 300 cube divided by 12 is equal to 450 into 10 to the power of 6 mm to the power of 4. Here h is equal to given. Here y1 is equal to 150 and yc is equal to 129. No? Here 129. So the difference is nothing but representing 150 minus 129 is equal to 21 mm. 20.9 mm is given. This is represented as H1 now. So Ig on x-axis is equal to Ig1x plus AH square, which is equal to 450 into 10 to the power of 6 plus 300 into 200 area, and multiplied by the distance between them is equal to 20.9, which is equal to 476.21 into 10 to the power of 4 mm to the power of 4 now. Similarly, the moment of inertia of circular section about an axis parallel to the x-axis here is given. Igdx is equal to pi d to the power of 4 divided by 64, which is equal to 24.85 into 10 to the power of 6 mm to the power of 4 now. Hd is equal to the distance between centroid of circular from the centroid of the composite section, which is equal to 200 minus 129.1, which is equal to 70.9. By substituting the values Igdx is equal to Igdx plus AH square, A2H2 square, we got the values is equal to 113.67 into 10 to the power of 6 mm to the power of 4. The moment of inertia of the combined section is obtained since the area is removed. It is the difference of Ig1xx minus Ig2xx. It is equal to 362.254 into 10 to the power of 6 mm to the power of 4. Okay, these are some of the important problems collected now, which deals with the determination of centroid for the plane areas, center of gravity for the solids, as well as the moment of inertia of the composite sections. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.